Astronomers were not searching for a new world when they found it. They were reviewing old telescope images, frames captured years earlier and quietly archived, when they noticed a faint point of light moving across the background stars in a way that made no sense. At first, it looked insignificant, just another frozen object at the edge of the solar system. But the more they measured its motion, the stranger it became. The object was enormous, roughly 700 kilometers across, large enough for gravity to pull it into the shape of a world. And yet its orbit was wrong, in a way astronomers struggle to explain using anything that should naturally exist here. Most planets and icy bodies in the solar system move along roughly the same flat plane, the ancient fingerprint left behind by the spinning disk that formed the Sun and planets 4.6 billion years ago. This object does not. Its path stretches thousands of astronomical units into deep space, tilted away from the solar system's normal architecture, like something dropped here from somewhere else entirely. And the most unsettling part is that one of the leading explanations says that may be exactly what happened. Some astronomers now believe this world was not born around our sun at all. They believe it formed around another star inside another planetary system before being torn away during a close stellar encounter billions of years ago, when the sun still lived inside a crowded nursery of newborn stars. A stolen planet, an object that crossed interstellar space and never went home. If that sounds impossible, the physics actually allows it surprisingly well under the right conditions. Young stars drift close together inside stellar nurseries. Their gravity overlaps. Planets can be exchanged the way passing ships exchange momentum across waves. And if this object truly came from somewhere else, then it means our solar system is not an isolated family that formed quietly and alone. It is a place shaped by encounters, theft, violence, and close gravitational calls with other stars long before Earth existed. It also means this may not be the only one. There could be other alien worlds orbiting our sun right now in the darkness beyond Neptune, hidden simply because we have not looked carefully enough yet. This channel grows because of people who take a moment to like and subscribe. If you enjoy these late night journeys through space, thank you for helping the channel continue. The story begins with the single rule our solar system was supposed to follow, and the object that appears to break it completely. Long before there were planets, there was only motion. A cold cloud of gas and dust drifted through the Milky Way about 4.6 billion years ago, stretched across trillions of kilometers, thin enough that you could have floated through it without noticing. But gravity was patient. Over immense spans of time, the cloud began collapsing inward under its own weight. The center grew hotter, denser, brighter. Eventually, pressure ignited nuclear fusion, and the sun was born. But the sun was not the whole story. The leftover material did not fall straight inward. The cloud had already been rotating, slowly at first, and as it shrank, that rotation accelerated. Conservation of angular momentum, the rule that spinning systems preserve their motion, forced the collapsing cloud to flatten into a broad disk. It happened for the same reason spinning dough spreads into a pizza shape beneath a cook's hands. Rotation resists collapse in certain directions. Inside that spinning disk, worlds began assembling. Dust grains collided. Pebbles became rocks. Rocks became mountain sized bodies. Over millions of years, gravity stitched those fragments together into planets, moons, asteroids, and icy debris. And because they all formed from the same rotating disk, nearly everything inherited the same basic motion. They orbit the sun in the same direction, along roughly the same flat plane. We call that plane the ecliptic. It is the solar system's fingerprint. Mercury follows it. Earth follows it. Jupiter, Saturn, Neptune, even most asteroids and comets obey it. Their orbits tilt slightly, but the overall structure remains remarkably orderly, like grooves cut into a spinning record billions of years ago. That order extends astonishingly far outward. Beyond the rocky inner planets sits the asteroid belt. Beyond that drift the gas giants, Jupiter and Saturn, wrapped in deep atmospheres of hydrogen and helium. Farther still are Uranus and Neptune, the ice giants. Past Neptune begins the Kuiper belt, a vast ring of frozen objects stretching from roughly 30 to 50 astronomical units from the Sun. One astronomical unit is about 150 million kilometers, the average distance between Earth and the Sun. It becomes our ruler out here. The Kuiper belt is filled with leftovers, icy bodies that never merged into full planets. Pluto lives there. Thousands of smaller worlds do too. But beyond it lies something stranger, the scattered disk, a sparse population of objects thrown outward by Neptune's gravity onto elongated and tilted paths. And then the distances become almost incomprehensible. Far beyond the scattered disk may exist the Oort cloud, a theoretical shell of icy bodies extending perhaps 100,000 astronomical units into darkness. Between those regions is mostly emptiness, mostly, because hidden among these distant populations is a class of object called a sednoid. Their orbits are so extreme, so detached from Neptune, that known planetary physics struggles to explain them. Their paths tilt at unusual angles. Their closest approaches remain impossibly distant. They do not behave like objects born peacefully within the solar system's original disk. And that leaves us with an uncomfortable possibility. What happens when an object appears in your solar system, but every rule says it should not belong there at all? For years, the object existed only as a mistake people overlooked. Its light appeared inside archived telescope images as a dim speck among thousands of brighter stars, so faint and slow that software systems treated it as background noise. Astronomers had photographed it repeatedly without realizing anything unusual was there. The data already existed. The discovery came later. A research team revisiting old survey images finally noticed the motion. They compared observations taken months apart from two different observatories, the Canada France Hawaii telescope on Mauna Kea and the Dark Energy camera in Chile. Against the fixed star field, one tiny point had shifted position almost imperceptibly. At first glance, the movement looked insignificant, but distant things move slowly. At roughly 90 astronomical units from the Sun, an object drifts across the sky with such patience that human observation struggles to notice it at all. One astronomical unit equals about 150 million kilometers, the average distance between Earth and the Sun. At 90 times that distance, sunlight itself arrives weakened and thin. The object received the designation 2017 OV 201. The year refers to when the original images were captured, not when astronomers understood what they contained. That understanding emerged gradually through orbital calculations and repeated confirmation. When the discovery was formally announced in 2025, planetary scientists immediately recognized that something about this world was deeply strange. Its size alone made it important. 2017 of 201 measures, approximately 700 kilometers across, large enough for gravity to compress it into a rounded shape that places it among the population of potential dwarf planets inhabiting the outer solar system. This is not a drifting fragment or irregular asteroid. It is a complete world, frozen and ancient. Its surface appears dark reddish brown. Spectroscopic observations, the study of light separated into wavelengths to identify chemistry, suggest a coating of methane ice Nitrogen ice and frozen carbon monoxide spread across the exterior. Mixed into those ices are compounds called tholins, complex organic materials created when ultraviolet radiation and cosmic rays bombard simple frozen chemicals over immense periods of time. Tholins are not biological, but they are chemically intricate, containing carbon rich molecular structures considered possible precursors to the chemistry life eventually depends upon. Similar materials stain Pluto and other distant icy bodies with muted red colors, giving the outer solar system its dim rusted appearance. And the cold there is almost absolute. Surface temperatures approach minus 230 degrees Celsius. At that temperature, substances that move freely through Earth's atmosphere become rigid solids. Nitrogen freezes, methane freezes, even carbon monoxide locks into ice. But none of these details became the true source of concern. Not the color, not the chemistry, not even the fact that a world this large remained hidden for so long. The real anomaly emerged from its orbit. 2017 of 201 takes roughly 25,000 years to complete one journey around the Sun, yet the shape and orientation of that path do not match the architecture expected from objects formed within the solar system itself. Its motion carries the signature of somewhere else. Astronomers reduce the mystery to two numbers, not its brightness, not its color. Two distances alone transformed 2017 of 201 from a distant curiosity into a serious problem for planetary science. Those numbers were its perihelion and aphelion, the closest and furthest points of its orbit around the Sun. Its perihelion lies at roughly 44 astronomical units. That means even at its nearest approach, the object barely enters the outer edge of the Kuiper belt. Neptune orbits at around 30 astronomical units, far inside this path. The object never comes close to the giant planets responsible for shaping most distant solar system bodies. But the second number is where the scale becomes unsettling. Its aphelion extends to approximately 1,600 astronomical units from the Sun, more than 50 times farther out than Neptune. At that distance, sunlight is almost meaningless, reduced to a dim point in overwhelming darkness. The object spends most of its existence there, drifting through regions where the Sun's gravity weakens toward interstellar space. One complete orbit takes about 25,000 years. The last time this world occupied its current position while moving inward, early modern humans were only beginning to spread beyond Africa. Entire civilizations rise and vanish in less than one fraction of a single orbit, but distance alone was not enough to trigger alarm. The orbit is also tilted. Its inclination, the angle between its orbit and the flat plane of the solar system, measures roughly 20 degrees. Many objects possess tilted orbits. Comets do, asteroids do, yet when that inclination combines with such an enormous detached orbit, the pattern stops looking natural, because Neptune should have controlled this region. For billions of years, Neptune has acted as the great gravitational sculptor of the outer solar system, disturbing or redirecting countless icy bodies beyond its orbit. Many Kuiper Belt objects carry the signature of repeated interactions with Neptune's gravity. Their paths stretch, shift, and scatter over immense spans of time, but Neptune's influence fades beyond roughly 50 astronomical units. 2017 of 201 remains too distant for Neptune to shape directly. Astronomers describe such objects as gravitationally detached, meaning no known planet currently reaches far enough to control their orbits. The object moves through a region that existing models struggle to explain, and it is not alone. Several Sednoid class objects share similarly extreme trajectories, and their orbital orientations display a suspicious clustering rather than random distribution. If these worlds reach their positions through chaotic scattering alone, their orbits should point in every direction equally. Instead, patterns appear. That leaves only a few serious explanations. Perhaps a hidden giant planet beyond Neptune is hurting these objects gravitationally. Perhaps a passing star disturbed the outer solar system during its youth, reshaping distant orbits long ago. Or perhaps some of these objects never formed around the Sun at all, but 2017 0201 introduced a complication immediately. Its orbital axis points the wrong way. The direction of its motion conflicts sharply with what one major hypothesis predicts. Before astronomers even finished calculating the orbit, one possibility had already begun collapsing under the weight of the numbers themselves. The idea began with a pattern nobody expected to see. Far beyond Neptune, several distant objects appeared to lean in the same direction, as though some unseen force had gently arranged their orbits over billions of years. Their paths through space were elongated, detached, and strangely aligned. Astronomers calculated the odds of that clustering happening randomly. The probability was about 0.007%. In January of 2016, planetary scientists Konstantin Batygin and Mike Brown at the California Institute of Technology proposed a dramatic explanation. A hidden planet far beyond Neptune might be sculpting these distant worlds through gravity alone. They called it Planet 9. The proposed world would not resemble Earth closely. Models suggested a mass between 5 and 10 times greater than our planet, orbiting somewhere between 400 and 800 astronomical units from the Sun. One complete orbit could require 10,000 to 20,000 years, and yet nobody has ever seen it. At roughly 600 astronomical units, even a large planet would reflect extraordinarily little sunlight. Planet 9, if it exists, would appear around 160,000 times fainter than the dimmest stars visible to the naked human eye. It would drift through darkness almost invisibly, moving so slowly that years of observations might reveal only the slightest positional change. Still, the search intensified. The Subaru telescope in Hawaii began systematic surveys of distant sky regions. Other observatories joined the effort. In 2025, the Vera Rubin Observatory in Chile started its enormous sky survey, repeatedly imaging the visible southern sky with unprecedented sensitivity. Astronomers were not searching blindly. Planet 9 predicts a specific gravitational signature. If a massive unseen planet shepherds Sednoid class objects, their orbital poles, the invisible axes defining how their orbits tilt and orient through space, should cluster in a consistent direction. Gravity would gradually organize them into a recognizable pattern over immense timescales. Many objects appear to support that prediction, but 2017 of 201 did not. Its orbital pole points in almost the opposite direction from where Planet 9 models predict it should be. The mismatch is not subtle. It cuts directly against the expected gravitational influence. Even if Planet 9 exists somewhere in the darkness, it cannot easily explain why this object moves the way it does. The orbit points wrong. That distinction matters enormously. 2017 of 201 does not destroy the Planet 9 hypothesis entirely, because the earlier clustering evidence still exists, but it fractures the simplicity of the idea. The outer solar system may not contain one unified population shaped by one hidden planet. It may contain several overlapping populations, each carrying evidence of different histories. Some objects may indeed be responding to an undiscovered planet. Others may not belong to the same story at all. The Vera Rubin Observatory may eventually settle the question by surveying the sky uniformly rather than focusing on selected regions. Within the next decade, astronomers should know whether the clustering behind Planet 9 reflects a real gravitational structure or simply the distortions of incomplete observations. But for 2017 of 201, one conclusion already stands. If Planet 9 cannot explain the orbit, the answer may lie beyond the solar system itself. Most planets spend their lives anchored to starlight. They circle suns. They rise and fall through predictable seasons of warmth and shadow. Even in the outer solar system, distant worlds still belong to something bright enough to dominate their skies. But scattered across the Milky Way are planets with no sunrise at all. Astronomers call them rogue planets. A rogue planet is a planetary mass object no longer gravitationally bound to any star. It drifts freely through interstellar space, untethered, moving through the galaxy alone. Some began as ordinary planets inside young solar systems before violent gravitational encounters hurled them outward forever. Others may have formed directly from collapsing gas clouds, growing large enough to resemble planets, but never massive enough to ignite into stars. Either way, they wander, and there may be more of them than stars. Modern estimates suggest the Milky Way contains hundreds of billions of rogue planets. In 2023, astronomers analyzing data from the Kepler Space Telescope during its extended K2 mission concluded there may be at least one rogue planet for every star in the galaxy. Since the Milky Way contains roughly 100 to 400 billion stars, the implication is staggering. The darkness between stars may be crowded with worlds. Most of them cannot be seen directly. They emit almost no light. Instead, astronomers detect them through gravitational microlensing, a technique based on gravity bending light itself. When a massive invisible object passes precisely between Earth and a distant background star, its gravity briefly magnifies the star's light. The timing and shape of that brightening reveal the hidden object's mass. For a moment, the darkness gives itself away. Microlensing surveys such as MOA in New Zealand and OGLE in Chile have identified rogue planets ranging from bodies smaller than Earth to gas giants larger than Jupiter. Some likely possess thick atmospheres and deep internal heat. Others are frozen almost completely solid. But even isolated worlds are not entirely cold inside. Elements such as potassium-40, uranium-238, and thorium-232 decay radioactively within rocky interiors, releasing heat over billions of years. On larger rogue planets buried beneath thick shells of ice, that heat may preserve subsurface oceans of liquid water in total darkness. No sky above them, no star, only internal warmth surrounded by endless night. These planets move through the galaxy at typical velocities between 20 and 50 kilometers per second relative to nearby stars. At those speeds, crossing the distance between the Sun and Proxima Centauri would still require roughly 25,000 to 60,000 years. Interstellar space remains almost incomprehensibly empty. A rogue planet spends nearly all of its existence falling through vacuum, without atmosphere, sunlight, or gravitational home. 99.9999% of the volume between stars contains essentially nothing at all. Yet these worlds continue moving silently through it, crossing the galaxy over spans longer than complex life has existed on Earth. And during the Sun's earliest history, the distances between stars were far smaller than they are now. Young stars, once crowded closely together, packed into dense birth clusters where planetary systems formed side by side, separated not by several light years, but fractions of one. In that environment, drifting worlds would not remain isolated forever. Some would pass close enough for gravity to intervene. Tonight, the nearest star to us is more than 4 light years away. That distance feels permanent when you stand beneath the night sky. Stars appear isolated from one another, scattered across enormous darkness, with almost unimaginable emptiness between them. But the sun did not begin its life in solitude. It was born crowded. Astronomers now believe the solar system formed inside a stellar nursery, a cold, giant molecular cloud filled with dense gas and dust where gravity triggered thousands of stars into existence at nearly the same time. These nurseries are chaotic regions, turbulent and bright, where newborn stars ignite beside one another inside relatively compact volumes of space. Our sun emerged inside one roughly 4.6 billion years ago. Estimates suggest between 1,000 and 10,000 sibling stars formed alongside it. In such environments, neighboring stars are often separated by only zero point 0.1 to 1 light year. Compare that to Proxima Centauri, currently 4.24 light years away from the Sunday. The early solar system lived in a crowded neighborhood. We know this not from direct observation, but from radioactive fingerprints preserved inside ancient meteorites. Some of the oldest rocks in the solar system contain traces of aluminium 26 and iron 60, unstable isotopes that decay rapidly on astronomical timescales. They could only have formed inside a nearby supernova. A massive star exploded close to the young Sunday, close enough that the expanding shock wave likely compressed the surrounding gas cloud itself. Estimates place that explosion between zero point 0.1 and zero point 0.3 light years away, near enough to influence the collapse of the solar nebula before the isotopes decayed into stable elements. The solar system formed inside violence. But birth clusters do not last forever. Over roughly 100 to 300 million years, gravitational interactions gradually fling stars outward into the wider galaxy. The original cluster dissolves. Sibling stars drift apart until their common origin becomes almost impossible to reconstruct. Before that dispersal happened, close encounters were common. Computer simulations published between 2018 and 2024 consistently show that a sun-like star inside a typical birth cluster should experience between 3 and 8 stellar flybys within roughly 1,000 astronomical units during the cluster's lifetime. On cosmic scales, those are intimate encounters, and the outer solar system still carries scars from them. The Kuiper belt ends abruptly around 48 astronomical units instead of fading smoothly outward, as many early formation models predicted. That sharp truncation resembles the effect expected if another star passed close enough to strip material away from the young outer disk through gravity alone. The geometry fits. So does the timing. Inside a dense birth cluster, thousands of young planetary systems would have been forming simultaneously, each ejecting debris, failed planets, icy bodies, and unstable worlds during their own periods of gravitational upheaval. Rogue planets, drifting between neighboring stars, would not have been rare exceptions there. They would have been natural byproducts of formation itself. And the distances separating those systems were small enough for gravity to begin trading material between them. Not metaphorically, literally. The young sun moved through an environment where wandering worlds could drift close enough to become trapped, captured not by intention, but by the crowded mathematics of stars forming together in the same small region of the galaxy. At first glance, the entire idea seems impossible. Gravity can pull objects inward, bend trajectories, even fling worlds across solar systems. But under normal conditions, a star cannot simply capture a passing planet. The mathematics refuses to allow it. In a two-body encounter, the outcome is reversible. A rogue planet approaching a star accelerates as gravity pulls it inward. It swings around the star, gains speed during the fall, then loses that same speed while climbing back outward. By the time it escapes, it leaves at essentially the same velocity it arrived with. Nothing has changed except direction. The object keeps going. For capture to happen, something must remove energy from the encounter. A third gravitational participant has to intervene, absorbing part of the rogue planet's motion, so escape becomes impossible. Without that extra interaction, the planet always flies away. This is called a three-body interaction. Inside the Sun's birth cluster, those conditions were unusually common. A rogue planet drifting between young stars could wander into the Sun's gravitational neighborhood while another massive object passed nearby. That second object might be a sibling star. It might also be Jupiter, and Jupiter mattered enormously. With roughly 318 times Earth's mass, Jupiter became the dominant gravitational force in the young solar system after the Sun itself. Analysis of ancient iron meteorites now suggests Jupiter formed within the first 1 to 2 million years of solar system history, early enough to participate directly during the crowded cluster phase. Imagine the geometry slowly unfolding. A rogue planet approaches the Sun from interstellar space. The Sun bends its path inward. But before the object can escape again, Jupiter or a nearby star steals a fraction of its kinetic energy, the energy carried by motion itself. The rogue planet slows slightly. Its trajectory changes from an open curve into a closed orbit. Not a collision, not an impact, just altered mathematics. The resulting orbit would not appear neat or orderly. A captured object retains much of the energy and direction from its original approach, producing a long elliptical path with a distant aphelion and a tilted inclination. The orbit would remain detached from Neptune because Neptune never created it. This matches 2017 of 201 remarkably well. Its orbit stretches thousands of astronomical units outward. Its inclination tilts away from the solar system's primary plane. Its perihelion remains too distant for Neptune to shape effectively. The orbital structure resembles exactly what gravitational capture predicts. And timing matters. Once the Sun's birth cluster dispersed and neighboring stars drifted apart, opportunities for three-body capture collapsed rapidly. Stellar encounters became rare. Rogue planets still passed through interstellar space, but the gravitational conditions necessary for permanent capture almost vanished. The window was temporary. A study published in 2024 simulated capture rates inside solar-type birth clusters and found something surprising. The probability of a young star capturing at least one distant object comparable in size to 2017 OF 201 ranged between roughly 20 and 40%. Not extraordinary odds, which means the orbit of this distant frozen world may not require exotic physics or unlikely coincidence at all. It may simply preserve the expected signature of how crowded, chaotic star formation naturally behaves. Before it belonged to the Sun, it belonged to another sky. Somewhere in the Milky Way, between 4.5 and 5 billion years ago, a different star formed inside its own spinning disk of gas and dust. Far from that star's warmth, in the frozen outer regions where temperatures remained brutally low, small grains of ice and rock slowly gathered together. Methane condensed there, nitrogen condensed there, carbon monoxide froze directly onto solid surfaces. A distant world began assembling in darkness. Over millions of years, gravity pulled those materials into a rounded body, roughly 700 kilometers across. The chemistry preserved on 2017 of 201 today still reflects that birthplace, because such volatile ices can survive only in extremely cold formation zones, far from stellar heat. But the star that made it is lost to us. The Milky Way contains hundreds of billions of stars moving constantly through the galaxy, orbiting its center over immense spans of time. Even if that original star still exists, it carries no visible marker, identifying it as the birthplace of this object. Whatever system first surrounded this world has long since scattered into the broader motions of the galaxy. Then the system became unstable. Young planetary systems are violent places. Giant planets migrate. Smaller worlds are perturbed repeatedly through gravity. Over time, those interactions slowly reshape entire orbital architectures. In the birth system of 2017 of 201, one of those long gravitational chains likely pushed the object farther and farther outward. Not suddenly, gradually. Its orbit stretched over millions of years until it stopped closing entirely. At some point, the object crossed the gravitational boundary where its parent star could no longer hold it. The world drifted free into interstellar space. No explosion marked the moment, only silence. Without nearby starlight, the surface temperature collapsed toward near absolute zero. Geological activity slowed and eventually ceased. The most volatile ices froze permanently into place. The surface entered a deep, frozen state that may have remained almost unchanged ever since. And then it wandered, perhaps for millions of years, perhaps far longer. The object crossed interstellar darkness alone, moving through the empty regions between stars while the galaxy slowly rotated around it. Eventually, during the era when the sun still lived inside its crowded birth cluster, the drifting world passed close enough for gravity to intervene once more. The capture itself would have looked uneventful. No impact occurred. No bright flash announced the transition. But through a three-body interaction involving the young sun and another massive object, likely Jupiter or a nearby sibling star, enough energy was removed from the object's trajectory to prevent escape. Its path bent inward permanently. A line through space became an ellipse. For the next 4 billion years, 2017 OF 200, one circled a star that did not create it, completing one orbit roughly every 25,000 years. During those silent revolutions, life on Earth changed from single-celled organisms into fish, forests, mammals, and eventually into a species capable of detecting a dim moving point in archived telescope images and asking where it came from. Long before astronomers discussed captured planets around the sun, there was already a captured world orbiting Neptune. You can see it tonight through large telescopes, faint and cold beside the outermost giant planet. Its name is Triton, Neptune's largest moon, discovered by British astronomer William Lassell on October 10th, 1846, only 17 days after Neptune itself was identified. Almost immediately, something about Triton looked wrong. Every large moon formed beside a planet should orbit in the same direction that planet rotates. This happens naturally when moons emerge from the same spinning disk of gas and debris surrounding a young planet. Shared formation creates shared motion, but Triton moves backwards. Astronomers call this a retrograde orbit, meaning the moon circles opposite Neptune's rotation. That single fact carries enormous consequences. Triton could not have formed alongside Neptune because the physics of planetary disks does not produce large retrograde moons naturally. It had to arrive later. The moon itself resembles the frozen bodies of the outer solar system far more than a typical planetary satellite. Triton's surface contains nitrogen ice, methane ice, and carbon dioxide frost spread across an intensely cold landscape. Its density, roughly 2 grams per cubic centimeter, suggests a composition of about 70% rock and 30% ice, closely matching large Kuiper belt objects. In many ways, Triton resembles Pluto more than it resembles a conventional moon. The leading explanation begins with a binary object, two icy bodies orbiting one another while drifting through the outer solar system. At some point billions of years ago, that pair passed close to Neptune. Gravity disrupted the system violently. One body gained energy and escaped outward into space. The other lost energy and became trapped permanently around Neptune. That trapped object became Triton. The exchange solved the same physics problem involved in capturing rogue planets. Without a third body participating, permanent capture cannot happen. But in a binary interaction, one object can carry energy away while the other remains behind. The consequences were catastrophic. Before Triton arrived, Neptune almost certainly possessed its own original moon system formed during the planet's birth. Triton's capture destabilized that arrangement completely. Simulations suggest many earlier moons were either destroyed through collisions or ejected from Neptune's gravity altogether as Triton's orbit settled over time. A captured world rewrote the entire system. Even now, the process is not finished. Triton's retrograde orbit creates tidal friction, slow gravitational interactions between the Moon and Neptune that gradually drain orbital energy. As a result, Triton continues spiraling inward. In roughly 3.6 billion years, it should cross the Roche limit, the distance where Neptune's tidal forces become strong enough to tear the Moon apart. It will become rings. So when we ask whether the Sun could capture a distant world, we are no longer discussing theoretical mathematics alone. We already possess direct evidence that gravitational capture reshapes planetary systems permanently. Triton remains orbiting Neptune today as proof, not a possibility, a precedent. And if capture could transform an entire moon system around Neptune, then capture operating on a larger solar system scale no longer feels extraordinary. It begins to look like a natural consequence of gravity acting patiently across enough time. Light carries memory. When sunlight reaches 2017 OF 201, a tiny fraction reflects back across 13.5 billion kilometers of space toward Earth. Astronomers capture that faint reflected glow and separate it into wavelengths, a technique called spectroscopy. Each chemical absorbs light differently, leaving distinct dark bands inside the spectrum. In this way, chemistry becomes visible at a distance. The surface spectrum of 2017 OF 201 already reveals several frozen compounds with surprising clarity. Astronomers have identified methane ice, nitrogen ice, carbon monoxide ice, and complex reddish organic materials known as tholins. These are not random coatings. They are environmental records preserved in deep cold. Nitrogen ice matters especially. Nitrogen freezes solid only under extremely low temperatures, meaning the object formed far from meaningful stellar heat inside the outer region of a protoplanetary disk. The same pattern appears on Pluto, Charon, Eris, and Makemake, large frozen worlds occupying the remote edge of our own solar system. At first glance, the chemistry feels familiar. But familiarity creates a deeper problem. Conditions in the outer regions of planetary disks may resemble one another across the galaxy. Cold is cold everywhere. Ultraviolet radiation interacts with ice similarly around many stars. Surface chemistry alone can suggest an environment, but it cannot identify a birthplace with certainty. The real forensic evidence may lie deeper inside the ice itself. Astronomers are particularly interested in isotope ratios, tiny variations in atomic structure preserved during formation. One crucial measurement involves deuterium, a heavier form of hydrogen containing an extra neutron. Water ice, formed under different temperatures and chemical conditions, acquires different deuterium to hydrogen ratios. Those ratios act like fingerprints. Oxygen isotopes provide another clue. Molecular clouds across the galaxy do not share perfectly identical chemistry because each cloud inherits material from different generations of dying stars. As a result, planets forming around different stars can preserve subtly different isotopic signatures inside their rocks and ices. If 2017 OF 200 one formed elsewhere, the evidence may still remain locked within its frozen surface. But measuring those ratios is extraordinarily difficult. At 90 astronomical units, the object reflects only a minute amount of sunlight. Current telescopes can identify broad surface compounds, yet detecting precise isotopic differences requires far greater sensitivity. The signal is simply too faint. A spacecraft could solve that problem. A flyby mission similar to New Horizons at Pluto could carry infrared spectrographs and mass spectrometers capable of analyzing the surface directly during close approach. Within a single encounter, scientists could compare isotopic ratios against known solar system values and determine whether the object truly shares our solar system's chemical ancestry, or whether it does not. That possibility changes the meaning of the surface entirely. If the isotopes differ significantly from solar system norms, then the tholins coating this world were not produced under our sun at all. They formed beneath another star, inside another molecular cloud, long before Earth existed. The chemistry frozen onto 2017 OF 200 one would become something extraordinary, not merely ancient material, but physical matter carrying the preserved environmental signature of a different solar system entirely. 2017 of 201 is strange, but it is not alone. Far beyond Neptune, astronomers have found a small collection of worlds occupying orbits that conventional solar system models struggle to explain. These objects belong to a category called sednoids, distant bodies whose trajectories remain detached from Neptune's gravitational influence and whose existence points towards something larger hidden in the solar system's history. The first known member appeared in 2003. On November 14th of that year, astronomers Mike Brown, Chad Trujillo, and David Rabinowitz identified a faint moving object using the Samuel Oschin telescope at Palomar Observatory in California. They named it Sedna, after the Inuit goddess associated with the cold depths of the Arctic Ocean. The orbit immediately caused confusion. Sedna measures roughly 1,000 kilometers across, making it larger than 2017 OF 201 and the largest confirmed sednoid known today. Its path carries it inward to 76 astronomical units from the Sun before extending outward again to roughly 937 astronomical units. One full orbit requires around 11,400 years, but the real problem was location. Sedna passed too far from Neptune for Neptune to shape its orbit effectively, yet it also remained far too close to belong to the distant Oort cloud population traditionally invoked to explain long period comets. Existing models predicted that region should contain almost nothing. Mike Brown later described the discovery plainly. Sedna should not exist. Almost immediately, astronomers proposed three possible explanations. Perhaps a passing star distorted the outer solar system early in its history. Perhaps an unseen giant planet still lurked in the darkness beyond Neptune, or perhaps Sedna originated somewhere else entirely and was captured later. The same possibilities still surround 2017 OF 201 today. Another object strengthened the mystery in 2014. Astronomers Scott Shepard and Chad Trujillo announced the discovery of 2012 VP 113 using observations from the Gemini Observatory and other facilities. Informally nicknamed Biden because of its designation letters, the object possessed an even more detached orbit than Sedna itself. Its perihelion sits around 80 astronomical units. Its aphelion extends roughly 450 astronomical units outward. Again, Neptune could not easily explain the trajectory. But when researchers plotted the orientations of Sedna, VP 113, and several similar bodies together, something unexpected appeared. The orbits seemed clustered. Instead of pointing randomly across space, many aligned in suspiciously similar directions. That statistical pattern later became the foundation for the Planet 9 hypothesis proposed by Konstantin Batygin and Mike Brown in 2016. Now, the picture has become less tidy. 2017 OF 200. One does not fit the same orientation pattern cleanly. Its orbital geometry points elsewhere, suggesting the sednoids may not represent one coherent population shaped by a single hidden planet. Some objects may share one origin. Others may preserve evidence of entirely different events. The family may be mixed. And within the coming decade, the Vera Rubin Observatory is expected to discover dozens more sednoid-class objects. Each new orbit will sharpen the pattern or fracture it further, slowly revealing whether these distant worlds share one history or many overlapping ones written together at the edge of the solar system. The outer solar system looks quiet now. Frozen objects drift slowly beyond Neptune, separated by enormous distances and moving along paths that barely change across human lifetimes. But those distant regions preserve evidence of an earlier period when the architecture of the solar system became violently unstable. The record is written in orbits. Astronomers call the leading explanation the Nice model, named after the city of Nice in France, where the framework was developed in 2005 by Rodney Gomes, Harold Levison, Alessandro Morbidelli, Cleomenes Tsiganis, and their collaborators. The model proposes that the giant planets did not always occupy their present locations. They migrated. Roughly 600 million years after the solar system formed, Jupiter and Saturn drifted into a 2-to-1 orbital resonance. Saturn completed one orbit around the Sun for every two completed by Jupiter. That repeated gravitational interaction destabilized the entire outer solar system. The consequences spread everywhere. Uranus and Neptune were pushed outward into new positions. Vast populations of icy bodies were scattered in all directions. Some objects were flung into deep space. Others plunged inward toward the Sunday. The orderly structure of the early Kuiper belt fractured under the rearrangement. We still see the aftermath today. On the Moon, Apollo astronauts collected ancient rocks, preserving evidence of an intense bombardment period between roughly 3.8 and 4.1 billion years ago. Astronomers call this episode the Late Heavy Bombardment, a surge of asteroid and comet impacts likely triggered by the migration of the giant planets. The outer solar system suffered its own disruption simultaneously. Many Kuiper belt objects were thrown into elongated orbits, creating the scattered disk population that still feeds long-period comets toward the inner solar system today. But some bodies survived by falling into orbital resonances with Neptune, repeating gravitational patterns that protected them from ejection. Pluto belongs to one of those protected groups. It occupies a 3 to 2 resonance, completing 2 orbits around the Sun for every 3 made by Neptune. Farther outward, another population survives within a 2 to 1 resonance. These objects avoided destruction not through stability, but through carefully balanced motion inside the chaos. Even the Kuiper belt's outer boundary carries scars. The belt ends sharply near 48 astronomical units instead of fading gradually into space. A smooth protoplanetary disk should not produce such an abrupt edge naturally. Current models suggest Neptune's outward migration swept material inward, while a passing star may have stripped material away from outside simultaneously. The edge itself remembers disruption, but 2017 of 201 may have remained largely untouched by all of it. If capture occurred during the Sun's birth cluster phase, the object would already have occupied its distant, detached orbit long before the nice model instability unfolded. Too far away to participate directly, while giant planets migrated, resonances shifted, and countless smaller worlds were scattered or destroyed. This captured object continued, tracing its immense 25,000-year orbit in darkness beyond the upheaval. The solar system around it was being broken apart and rebuilt into the structure we recognize today. Its orbit endured unchanged. In that sense, 2017 OF 201 may preserve not only evidence of capture, but a frozen orbital memory from before the solar system settled into its modern form. For most of modern astronomy, interstellar objects were theoretical. Scientists assumed they existed because planetary systems should eject enormous amounts of debris during formation, but no one had ever directly observed an object entering the solar system from another star. The idea remained mathematical, distant, almost abstract. Then, in 2017, one finally appeared. On October 19th, astronomer Robert Warwick identified a faint moving object using the Pan-STARRS telescope at Haleakala Observatory in Hawaii. At first, it seemed ordinary, but calculations quickly revealed something unprecedented. Its orbit was hyperbolic, meaning the object possessed too much velocity to remain gravitationally bound to the sunday. It came from outside the solar system. Astronomers designated it 1I/Oumuamua. The prefix stood for first interstellar, a completely new classification created specifically because no confirmed extrasolar object had ever been seen before. Its trajectory was extraordinary. Oumuamua entered the solar system from the direction of the constellation Lyra and passed within 0.255 astronomical units of the Sun on September 9, 2017, well inside Mercury's orbit. By the time astronomers discovered it, the object was already leaving again, and it looked unlike anything familiar. As Oumuamua rotated, its brightness changed dramatically, producing a strange light curve that suggested an extremely elongated or flattened shape. Estimates implied proportions perhaps 6 to 10 times longer in one dimension than another, more extreme than typical asteroids or comets observed inside our solar system. But shape was only the beginning. As the object moved outward, astronomers noticed slight additional acceleration beyond what solar gravity alone predicted. Normally, such acceleration comes from cometary outgassing, jets of evaporating material pushing the body gently through space. Yet telescopes detected no visible coma, no dust tail, no obvious gas release. The anomaly became famous. Several explanations emerged. Invisible hydrogen outgassing remained plausible. Radiation pressure from sunlight acting on an unusually thin geometry was another possibility. A far more speculative interpretation, heavily amplified outside the scientific community, suggested an artificial light sail. Most astronomers rejected that conclusion. Then another visitor arrived. On August 30th, 2019, amateur astronomer Gennady Borisov detected a second confirmed interstellar object from his observatory in Nauchny, Crimea. Designated 2I/Borisov, this object behaved far more conventionally. It looked like a comet. Roughly 500 meters across, Borisov displayed a bright coma and dust tail produced by ordinary outgassing as sunlight heated surface ice. Spectroscopic observations revealed carbon monoxide and water vapor broadly similar to the chemistry found in solar system comets. Its orbit, however, remained unmistakably extrasolar. The discovery of two interstellar objects within only 3 years changed astronomy immediately. Earlier estimates had assumed such visitors would be exceedingly rare, but the detection rate implied the galaxy may contain vastly more drifting objects than expected, perhaps enough that Oumuamua-sized bodies occupy interstellar space at densities approaching 1 per cubic astronomical unit. The galaxy suddenly felt crowded. But both objects shared one crucial characteristic. Their paths remained open. Hyperbolic trajectories guaranteed escape. They entered the solar system temporarily, crossed through it, and continued back into interstellar darkness. 2017 of 201 may represent the opposite outcome entirely. Not a visitor passing through, but a visitor that arrived during the right gravitational conditions, lost just enough energy, and never left again. From Earth, 2017 OF 201 appears only as a faint moving point of reflected sunlight. But beneath that frozen surface may exist a fully layered world, shaped internally by the same physical processes that formed planets and moons throughout the solar system. Size changes everything. At roughly 700 kilometers in diameter, the object is large enough that its own gravity likely reorganized its interior over billions of years. Astronomers call this differentiation, the process where denser materials sink inward while lighter materials rise upward. Earth experienced the same transformation long ago. Inside 2017 OF 201, heavier rocky compounds probably settled toward the center, perhaps forming a compact silicate core with a smaller iron-rich region buried deeper still. Above that core, models suggest a thick mantle dominated by water ice. Closer to the surface, more volatile compounds such as methane, nitrogen, and carbon monoxide would freeze into layered crusts exposed directly to space. And above everything else rests radiation chemistry. For billions of years, ultraviolet light and cosmic rays have altered the uppermost ice layers, slowly manufacturing the reddish organic compounds called tholins that now coat the surface. Those compounds may extend only a thin distance downward, preserving older, untouched material beneath. But the interior may not be completely frozen. Even isolated worlds contain internal heat sources, radioactive isotopes such as potassium-40, uranium 238, and thorium 232 decay naturally over immense spans of time. Each decay releases small amounts of energy. Across billions of years, that heating accumulates inside rocky bodies. The process never fully stops. Pluto provides an important comparison. Data from the New Horizons spacecraft revealed unexpectedly young terrain and unusual tectonic features, suggesting a liquid water ocean may still survive beneath Pluto's outer ice shell. Pluto is much larger than 2017 of 201, measuring roughly 2,377 kilometers across, yet the underlying physics remains similar. Smaller worlds can still retain heat. If enough radioactive energy persists within the core, a subsurface ocean could survive beneath layers of compressed ice, insulated from the near absolute zero temperatures above. Liquid water in direct contact with rock creates hydrothermal chemistry, reactions similar to those occurring near deep-sea volcanic vents on Earth. Some origin of life researchers consider those environments especially important. There is no evidence that life exists inside 2017 OF 201. None. Life likely requires far more stable and complex conditions than liquid water alone. But chemically speaking, an ocean bearing rocky minerals and internal heat would not be categorically less interesting than environments already studied on Europa or Enceladus. The surface above that hidden interior may preserve even older records. Without weather, erosion, rainfall, or plate tectonics, impact craters remain frozen into place for unimaginable spans of time. Cosmic rays slowly damage exposed molecules. Occasional collisions scar the crust. Otherwise, almost nothing changes. The preservation is extraordinary. Some surface regions may have remained largely undisturbed since before the Earth fully formed. Every crater, every ice layer, every trapped molecule exists inside a world held in suspended geological time by cold, darkness, and distance from the sun that did not create it. Nothing about 2017 OF 201 is stationary. Even now, while we observe it from Earth, the object is descending slowly inward through the outer darkness of the solar system, following an orbit that has been unfolding for millions of years before human beings ever looked upward. Its motion is patient. At present, the object remains roughly 90 astronomical units from the Sun, still far beyond Neptune and deep inside the cold frontier where sunlight weakens into little more than a distant glow. But gravity never fully releases its hold. Over the coming millennia, 2017 OF 200, one will continue falling inward until it reaches perihelion, the closest point in its orbit around the Sun, at roughly 44 astronomical units. Even there, it never approaches warmth. The sunlight at that distance remains extraordinarily faint compared to conditions inside the inner solar system. Yet small changes matter across frozen worlds. As solar radiation slowly intensifies, the most volatile surface compounds begin responding first. Astronomers call this sublimation. Sublimation occurs when a substance transforms directly from solid into gas without passing through a liquid state. Different ices activate at different temperatures. Carbon monoxide ice sublimates at roughly 25 Kelvin. Nitrogen ice follows near 35 Kelvin. Methane requires temperatures closer to 50 Kelvin before significant evaporation begins. Water ice remains frozen throughout the entire journey. As these volatile compounds escape the surface, they carry microscopic dust grains upward into space, creating a thin atmosphere around the object known as a coma. Unlike the bright comas of inner solar system comets, This one would likely remain faint and diffuse, barely detectable except through powerful instruments. But scientifically, the coma matters enormously. The escaping gas contains material preserved beneath the radiation damaged outer crust, compounds isolated since the earliest stages of planetary formation. Some molecules may not have interacted directly with sunlight for billions of years. Now, for a brief interval, they drift freely into surrounding space, where telescopes can analyze them. Spectroscopy becomes crucial again. By separating that faint light into its component wavelengths, observatories can identify specific gases released during sublimation. Instruments aboard the James Webb Space Telescope may eventually detect molecular signatures impossible to measure from the frozen surface alone, including subtle compounds hidden beneath the upper ice layers. And the timing is unusually fortunate. Perihelion occurs within the operational lifetime of current observatories, making this an active scientific opportunity rather than a distant future prediction. The object is approaching close enough for humanity to study chemical processes unfolding in real time. But the activity will not last. After reaching perihelion, gravity begins pulling the object outward once more. The inward fall reverses. Temperatures slowly decline again across the surface. The coma weakens as gases refreeze onto the crust. Carbon monoxide freezes first, then nitrogen, then methane. Eventually, the atmosphere disappears entirely. Silence returns. 2017 of 200. One will spend another 12,500 years retreating toward its aphelion near 1,600 astronomical units from the sunday. By the time it returns inward again, every civilization alive today will have vanished into history, and the sky above Earth may belong to beings we cannot imagine. High in the Chilean Andes, above drifting cloud layers and desert air, almost completely stripped of moisture, a new observatory now watches the sky with a patience no human survey team could ever sustain. The mountain is called Cerro Pachon. At an altitude of 2,647 meters above sea level, the atmosphere above the summit remains unusually stable and dark for much of the year. These conditions matter enormously for astronomy. Dry air absorbs less infrared radiation. Minimal light pollution sharpens faint details. Steady atmospheric flow reduces distortion from turbulence. This is where the Vera Rubin Observatory was built. Its primary mirror measures 8.4 meters across, large enough to collect roughly 40 times more light per unit time than a typical survey telescope from the previous generation. But the mirror alone is not what makes the observatory transformative. The camera changes everything. Containing 3,200 megapixels, it is the largest digital camera ever constructed for astronomy. A single exposure captures an area of sky spanning roughly 40 full moons. Every image contains billions of stars, galaxies, asteroids, and distant moving points of light, too faint for earlier surveys to notice. And it never stops scanning. The observatory's central mission is called the Legacy Survey of Space and Time. Over 10 continuous years, the system will photograph the visible southern sky approximately every 3 nights, building an enormous time-lapse record of cosmic motion. Movement becomes visible through repetition. Objects like 2017 OF 201 are difficult to detect precisely because they move so slowly against the background stars. In a single night, they appear stationary. But when images separated by weeks or months are compared carefully, tiny positional shifts emerge. The Vera Rubin Observatory automates this process across the entire sky. Each night generates roughly 20 terabytes of raw imaging data, an information volume comparable to the text contents of the Library of Congress every 4 days. Advanced software systems then compare new images against previous observations, searching for subtle motion patterns impossible to identify manually. But sensitivity matters just as much as coverage. The observatory can detect objects approximately 100 times fainter than those visible to earlier wide-field sky surveys. That increase extends humanity's practical reach deep into the outer solar system, where sunlight becomes weak and reflected light nearly disappears. Astronomers expect remarkable numbers. Current catalogs contain roughly 3,500 known trans-Neptunian objects, bodies orbiting beyond Neptune. Over the Rubin survey's decade-long operation, researchers anticipate tens of thousands more discoveries. Some may resemble known populations, others may not. If 2017 OF 200 one belongs to a broader class of captured extrasolar objects, the Vera Rubin Observatory should begin revealing companions with similarly detached orbits and similarly unusual orbital orientations. Patterns will emerge statistically, not through one dramatic discovery, but through accumulation. And within about 10 years, the uncertainty surrounding these distant worlds may narrow sharply. Either the captured population becomes undeniable. 2017 OF 201 proves to be an isolated anomaly, or planetary science confronts a structure in the outer solar system that no existing model predicted correctly. Beyond the distant arc traced by 2017 OF 201, the solar system fades into a region no human being has ever directly observed. Not empty space. Something stranger. Astronomers call it the Oort cloud, a vast spherical shell of icy bodies surrounding the Sun at distances beginning around 2,000 astronomical units and extending, perhaps as far as 100,000 astronomical units, into interstellar darkness. At its furthest edge, sunlight takes more than a year to arrive. Yet no telescope has ever photographed it directly. The reason is brutally simple. Objects that distant reflect almost no light at all. Even a comet nucleus, 10 kilometers across, becomes effectively invisible against the background of deep space, fainter than many galaxies, billions of light years away. Current instruments cannot survey the region comprehensively, and no planned observatory changes that limitation. So, the Oort cloud is inferred indirectly. Long-period comets occasionally appear in the inner solar system on enormous elongated orbits, requiring origins far beyond the Kuiper belt. Their trajectories point outward toward an unseen reservoir surrounding the Sun from every direction. The cloud reveals itself only when gravity disturbs one of its frozen members and sends it falling inward. The numbers involved are staggering. Current estimates suggest the Oort cloud may contain between 100 billion and 2 trillion icy objects larger than 1 kilometer in diameter. The total mass remains deeply uncertain, somewhere between 1 and 100 Earth masses. The uncertainty spans a factor of 100 because the region itself remains fundamentally unobserved. Even its internal structure is theoretical. Astronomers divide it into two broad regions. The inner Oort cloud, also called the Hills cloud, occupies the zone between roughly 2,000 and 20,000 astronomical units. Objects there remain more tightly bound to the Sun gravitationally. Sedna's orbit reaches toward this territory. 2000, 17 of 200, one with its aphelion near 1,600 astronomical units, approaches its threshold without fully entering it. Further outward lies the outer Oort cloud. Here, gravity weakens dramatically. Passing stars can disturb objects from enormous distances away. Even the Milky Way itself begins exerting influence through something called the galactic tide, the subtle difference in gravitational pull acting across the immense diameter of the solar system. The effect accumulates slowly. Over millions of years, the galactic tide can alter distant comet orbits enough to send them spiraling inward toward the Sunday. Some become the long period comets visible from Earth. Others are lost entirely, stripped away into interstellar space by stellar encounters. But capture works both directions. If the young solar system could capture a world the size of 2017 OF 201 during its birth cluster phase, then countless smaller extrasolar objects were likely captured as well. Statistically, they should outnumber the larger bodies enormously. Many may still inhabit the unseen depths of the Oort cloud today. Invisible, uncatalogued. In that sense, the Oort cloud may already contain material formed around other suns, preserved beside native solar system debris for billions of years without distinction. The outermost shell surrounding our planetary system is not merely a boundary. It is an archive of gravitational history written in frozen objects too distant for us to read directly. Long after the Sun drifted away from its crowded birth cluster, the solar system continued moving through a galaxy filled with other stars, crossing their own enormous orbits around the Milky Way. The encounters never truly stopped. For most of human history, these passing stars seemed fixed and permanent against the night sky. But motion accumulates across deep time, and modern astronomy can now reconstruct those motions with extraordinary precision. The key instrument is Gaia. Launched by the European Space Agency in December 2013, the Gaia Space Telescope has measured the positions, distances, and three-dimensional velocities of more than 1.8 billion stars. With that information, astronomers can project stellar trajectories backward and forward through millions of years of galactic motion. Patterns begin appearing immediately. One of the most important discoveries involved Schultz's star, identified in 2013 by astronomer Ralph Dieter Schultz. The system consists of a small red dwarf accompanied by a dim brown dwarf companion, currently located about 22 light-years from Earth. But it was much closer once. Using Gaia measurements, astronomers determined that Schultz's star passed within approximately 0.82 light-years of the Sun around 70,000 years ago. That distance carried it directly through the outer region of the Oort cloud. The timing feels strangely intimate. When Schultz's star approached the solar system, anatomically modern humans already existed on Earth. Early people were creating tools, traveling across harsh landscapes, and watching unfamiliar constellations without any awareness that another star system was gliding silently through the outer darkness surrounding the Sunday. Its gravitational effects unfolded invisibly. At that range, Schultz's star likely disturbed thousands of icy Oort cloud bodies, altering trajectories accumulated over billions of years. Some objects may eventually drift inward as long-period comets millions of years after the original flyby itself, making the event impossible to recognize directly from Earth. And another encounter is already approaching. A star known as Gliese 710, a K-type dwarf containing roughly 60% of the Sun's mass, is currently about 64 light-years away. Gaia data confirms that it is moving toward the solar system on an unusually close trajectory. The predicted passage is remarkable. In approximately 1.29 million years, Gliese 710 is expected to pass within about 5,000 astronomical units of the Sun, penetrating deep into the inner Oort cloud itself. At that distance, Its gravity should trigger a substantial reshuffling of distant icy bodies. Comet activity will likely increase dramatically. Thousands of objects may be perturbed onto new orbits, carrying them gradually inward toward the planetary region over subsequent millions of years. Most will never approach Earth closely. But the architecture of the outer solar system will change again, quietly and permanently. And these encounters are not exceptional events. Across 4.6 billion years, the Sun has likely experienced hundreds of stellar flybys at varying distances and velocities. Some stripped material away, others perturbed comet reservoirs. A few may have delivered captured objects from beyond the solar system itself. The frontier surrounding our planetary system has never been sealed. It remains porous, dynamic, and exposed to the slow gravitational traffic of the galaxy around it. For most of the 20th century, planetary systems beyond our own existed mainly as theory. We could see stars. We could measure their light. But the disks and distant icy structures surrounding them remained hidden behind distance and glare. That changed in the Atacama Desert. Spread across 16 kilometers of northern Chile, the Atacama Large Millimeter Array, usually called ALMA, combines 66 radio antennas into a single coordinated instrument capable of resolving astonishing detail around young stars. Instead of visible light, ALMA observes millimeter wavelength radiation emitted by cold gas and dust. The cold regions become visible at last. In 2014, ALMA released one of the most important astronomical images ever produced, a detailed view of the young star HL Tauri, located roughly 450 light-years from Earth. The image showed concentric bright rings separated by dark gaps inside the surrounding protoplanetary disk. Those gaps changed planetary science immediately. They indicated that planets were already forming and clearing orbital paths through the disk less than 1 million years after the star itself formed. Previous models predicted a much slower process, but HL Tauri demonstrated that giant planets can emerge extremely early in stellar history. Early formation changes everything downstream. Massive young planets destabilize surrounding material gravitationally. Smaller icy bodies are scattered outward, some collide, others are ejected completely from their systems into interstellar space. Faster planet formation means earlier gravitational instability, and earlier instability means more time for stellar systems to populate the galaxy with rogue objects. And HL Tauri is not unusual. Space observatories, including Herschel and Spitzer, have detected excess infrared radiation around roughly 20 to 30% of Sun-like stars. This excess heat comes from dust generated by collisions inside distant belts of icy bodies, structures broadly analogous to our Kuiper belt. The implication becomes difficult to avoid. If Kuiper belt-like regions are common, then the icy populations inhabiting them must also be common. And if those populations exist around enormous numbers of stars, gravitational ejection should occur constantly throughout the galaxy. Surveys of giant exoplanets reinforce the same picture. Radial velocity measurements and direct imaging studies suggest that perhaps 10 to 20% of Sun-like stars host giant planets on wide orbits. These massive worlds disturb outer debris fields continuously over billions of years, slowly leaking objects outward into interstellar darkness. The galaxy behaves like an ongoing exchange system. Young planetary systems eject unstable debris during formation. Mature systems continue reshaping outer reservoirs through gravitational interactions. Aging stars disrupt surrounding orbits as they evolve. Everywhere across the Milky Way, planetary material drifts loose from its original birthplace. But chemistry remains surprisingly familiar. The interstellar comet Borisov carried carbon monoxide and water ice compositions broadly resembling solar system comets, despite forming around another star entirely. Astronomers sometimes describe this pattern as chemical homology, meaning planetary systems across the galaxy appear to share similar raw ingredients even when their detailed histories differ. So when we look outward now, we no longer see isolated stars forming independently in silence. We see overlapping systems, exchanging material across immense spans of time and distance, each contributing fragments to the broader galactic environment from which new worlds continue emerging. When we picture the outer solar system, it is tempting to imagine a region already mapped and understood, its major structures identified, and its populations largely catalogued. But that impression is deeply misleading. As of 2025, astronomers have confirmed roughly 3,500 trans-Neptunian objects, meaning bodies orbiting beyond Neptune. These are the worlds officially tracked, measured, and assigned stable orbital solutions. Yet this number describes only what we have managed to find. Current population estimates suggest the outer solar system contains approximately 100,000 trans-Neptunian objects larger than 100 kilometers across. That means humanity has detected only around 3.5% of the larger bodies likely present beyond Neptune. And below that size threshold, the numbers rise dramatically. Tens of millions of smaller objects probably occupy the Kuiper belt and scattered disk. Most remain completely uncatalogued. They are too faint, too distant, or too slow-moving for existing surveys to detect consistently. Then the scale expands again. The Oort cloud alone may contain between 100 billion and 2 trillion icy bodies, yet not one has ever been directly observed. Their existence is inferred entirely through orbital mechanics and the behavior of long-period comets entering the inner solar system from extreme distances. We are studying shadows of a population we cannot see. Part of the difficulty comes from detection bias, a problem woven into the history of observational astronomy itself. Survey telescopes have never monitored the entire sky continuously. Most searched only selected regions, usually near the plane of the solar system where astronomers expected objects to be concentrated. That expectation shapes discovery. Objects become easiest to detect when they approach the sun because reflected sunlight increases dramatically at closer distances. As a result, our catalogs are heavily weighted toward bodies currently near perihelion rather than representing a random sample of the outer solar system. The bias becomes even stronger for extreme objects. If captured extrasolar worlds occupy elongated, detached orbits, like 2017 OF 201, they spend almost all of their orbital lifetimes far beyond current detection limits. A body with a 25,000-year orbit may remain observable for only a tiny fraction of that cycle. Most of the population could therefore remain hidden. In some ways, the situation resembles dark matter research in cosmology. Astronomers know dark matter exists because of its gravitational influence, even though it has never been directly detected. Similarly, planetary scientists know enormous unseen populations inhabit the outer solar system because orbital behavior demands their presence. The Vera Rubin Observatory will improve this picture enormously, but even that observatory will not produce a complete inventory. It will simply increase the detected fraction enough for statistical conclusions to become far more reliable than they are today. And that distinction matters. The honest scientific position is not that the outer solar system is mysterious because we lack theories. It is mysterious because our observations remain fragmentary. We are drawing a map while still illuminating the landscape itself, and there is every reason to suspect that entire structures remain outside the edge of our current view. Deep beneath the frozen surface of 2017 OF 201, beyond the methane frost and ancient tholin crust, there may be a more profound clue waiting in silence. Not in the ice, in the rock itself. Stars do not all form from identical material. Every stellar nursery inherits a different chemical history, shaped by billions of years of galactic evolution. Molecular clouds absorb the debris of earlier stars, material expelled through supernova explosions and stellar winds, then recycle that matter into new systems. The galaxy changes chemically over time. That means the composition of a planetary system depends partly on where and when its parent star formed. Some molecular clouds contain larger proportions of oxygen, others contain more carbon. Those ratios alter the minerals that can exist as planets begin to assemble inside protoplanetary disks. In our own solar system, the Sun's carbon to oxygen ratio is approximately 0.55. Oxygen is more abundant than carbon, so rocky material formed primarily from silicate minerals, compounds where oxygen bonds with silicon, magnesium, and iron. This is the geology you know from Earth: granite, basalt, olivine, quartz. But planetary chemistry changes dramatically if carbon becomes more abundant than oxygen. In systems where the carbon to oxygen ratio exceeds 1, oxygen becomes chemically exhausted before all the carbon can bond with it. The leftover carbon forms different minerals entirely. Instead of silicate rock, planets may contain silicon carbide, a hard crystalline compound more familiar on Earth as an industrial abrasive. Graphite layers could replace basaltic crusts. Carbon compounds might dominate the mantle chemistry of entire worlds, a different foundation for geology itself. Astronomers now estimate that roughly 10 to 15% of Sun-like stars possess elevated carbon abundances, potentially capable of producing these carbon-rich planetary systems. The number is large enough that such worlds are unlikely to be rare curiosities. They may be common throughout the Milky Way. And this returns us to 2017 OF 201. If it formed around a carbon-rich star billions of years ago, then its interior may contain minerals fundamentally unlike those found in any confirmed solar system object. Its rocky core would preserve a chemical environment shaped under another stellar composition, then carried across interstellar space before capture by the Sunday. The challenge is access. Surface ice alone cannot answer this question. The volatile coatings visible through spectroscopy reveal temperature history more readily than deep mineral composition. But silicon carbide and other carbon-rich compounds possess distinct infrared spectral signatures that a sufficiently close spacecraft could potentially identify. A flyby mission equipped with high-resolution spectrometers might settle the issue directly, and the implication would extend far beyond a single, distant world. If rogue planets and captured objects preserve the chemistry of their birth systems, then the solar system may already contain samples of planetary architectures that never formed here. Hidden in darkness beyond Neptune could be fragments of geologies that Earth-based planetary science has never encountered before. Our rocky world would stop being the template. It would become one example among many. Long before humans understood galaxies, we imagined worlds as isolated places, each sealed inside its own celestial borders. But physics does not recognize borders. Material moves constantly between planets, moons, comets, and stars. Dust drifts outward on radiation pressure. Impacts eject rock into space. Gravity trades objects between systems whenever stars pass close enough together. Over billions of years, the galaxy becomes less a collection of separate systems and more a slow exchange of matter across unimaginable distances. This is where the idea of panspermia enters the conversation. Panspermia is the hypothesis that life, or the chemical ingredients that support life, can travel between worlds. One specific version, called lithopanspermia, proposes that microorganisms trapped inside rocks blasted from a planetary surface by impacts could survive space travel and later land elsewhere. At first, the idea sounds impossible, but laboratory experiments have repeatedly shown surprising biological resilience. Certain bacterial spores can survive vacuum exposure, intense cold, dehydration, and high radiation doses. Tardigrades, microscopic animals known for enduring extreme conditions, have survived direct exposure to space during orbital experiments. Even meteorites support the principle. Fragments blasted from Mars by impacts have been found on Earth, proving that rocky material can naturally travel between planets. Some meteorites preserve complex organic molecules after atmospheric entry, despite the violence of the descent. But interstellar travel introduces a much harder problem. The distances between stars are enormous, and travel times span millions or even hundreds of millions of years. Cosmic radiation gradually damages biological molecules over these durations. No confirmed organism has demonstrated survival on anything close to such timescales. Still, some researchers argue that large rocks may provide shielding deep enough to reduce radiation damage dramatically. A microorganism buried hundreds of meters beneath the surface of an ejected object could remain protected for extraordinary lengths of time. The evidence remains incomplete, but the physics is not forbidden. Even without living organisms, 2017 OF 200, one almost certainly carries complex organic chemistry. The tholins coating its surface, formed through long exposure to ultraviolet radiation and cosmic rays acting on simple, frozen compounds. These reactions produce increasingly complicated carbon-based molecules, some chemically similar to precursors involved in biological chemistry on Earth. Not life, but chemistry moving toward complexity. And material from the outer solar system does not stay isolated forever. Jupiter continuously perturbs distant icy bodies inward. Long-period comets cross the planetary region, shedding dust, gas, and microscopic particles throughout the inner solar system. Some eventually intersect Earth, so the chain becomes difficult to dismiss entirely. A world forms around another star. It is ejected into interstellar space. Later, it is captured by the Sunday. Over billions of years, impacts release fragments from its surface. Some drift inward. Some may eventually reach Earth. Each individual step is physically plausible. The overall sequence remains speculative. There is no evidence linking 2017 OF 201 to biology on Earth, and no serious scientist would claim otherwise. But the broader implication lingers quietly beneath the discussion. Solar systems are not closed containers. From the beginning, matter has been crossing between them. Somewhere in the Milky Way, a star once illuminated the surface of 2017 OF 201. That much seems likely. But whether that star still exists is another question entirely. Stars do not all age the same way. Their lifespans depend almost completely on mass. Massive stars burn through nuclear fuel rapidly, radiating enormous energy before collapsing after relatively short lives. Smaller stars consume fuel slowly and can survive for hundreds of billions, even trillions, of years. The Sun sits between these extremes. A star similar to the Sun lives for roughly 10 billion years before exhausting the hydrogen in its core. Since 2017 of 200, one likely formed between 4.5 and 5 billion years ago, a Sun-like parent star would still exist today, still shining somewhere in the galaxy. But identifying it would be effectively impossible. The Milky Way contains between 100 billion and 400 billion stars, all moving continuously through galactic space. Over billions of years, stellar orbits drift, scatter, and reshape under gravity. The original system has long since disappeared into the crowd, but the possibilities become stranger if the birth star was larger than the Sunday stars, exceeding roughly 8 solar masses, end their lives violently as supernovae. A star 10 times more massive than the Sun survives only about 20 million years before core collapse triggers an explosion bright enough to briefly outshine entire galaxies. In that scenario, the parent star of 2017, OF 201, may have died before Earth even formed. Its planetary system would not have survived intact. The expanding shock wave and sudden mass loss from the explosion would destabilize remaining planetary orbits, ejecting some worlds into interstellar space while destroying others completely. An entire solar system erased in seconds. But 2017 OF 201 itself may never have witnessed that ending. If it had already been ejected during early gravitational instability, it would have drifted through darkness long before the star exploded behind it. The system would have died without it. There is another possibility as well. Stars with masses similar to or smaller than the Sun die more quietly. They expand into red giants, shedding their outer layers over millions of years before collapsing into white dwarfs, dense stellar remnants roughly the size of Earth. These white dwarfs slowly cool for billions of years afterward, fading gradually into darkness. If the birth star followed this path, it may still exist somewhere in the galaxy today as a cooling ember surrounded by emptiness. Its inner planets could have been consumed during the red giant phase. Outer worlds may have been destabilized or lost entirely, yet one fragment endured. The object now orbiting our Sun may be the final surviving remnant of a planetary system otherwise erased from existence. Its frozen surface may preserve chemical records older than Earth's oceans, older than the Moon, perhaps older than the solar system itself. And we cannot trace it home. The Sun travels around the Milky Way at approximately 220 kilometers per second. Over 4 billion years, the possible location of that lost parent star expands across tens of thousands of light years. Whatever system once called this world its own has vanished into the galaxy. Imagine the solar system before it became quiet. Not empty, not ordered, not stable. Around 4 to 4.5 billion years ago, the young Sun still lived inside its birth cluster, surrounded by thousands of neighboring stars packed within a region only a few light years across. Their light mixed faintly through enormous clouds of dust and gas. Around many of them, planetary systems were already forming, unstable and crowded, constantly exchanging debris through gravitational encounters. The galaxy was closer then, more crowded. Somewhere beyond the young Sun, 2017 OF 200, one was already alone. It had likely spent millions of years drifting through interstellar darkness after gravitational instability slowly pushed it beyond the reach of its original star. By now, its surface had frozen completely, coated in volatile ice beneath weak starlight from distant suns scattered across the cluster. Then its path bent slightly. At first, the effect was subtle. Across enormous distances, the sun's gravity began altering the object's trajectory, curving what would otherwise have remained a straight interstellar path. The acceleration was gentle, almost impossible to notice from the perspective of the object itself. But gravity accumulates over distance. As the rogue world moved deeper into the sun's gravitational neighborhood, another influence entered the geometry. A nearby sibling star may have passed within several hundred astronomical units, or perhaps Jupiter had already grown massive enough to shape the encounter directly. Now, three bodies shared the same moment. This is where capture becomes possible. In a simple two-body interaction, the object would swing around the sun and leave with the same energy it arrived with. The motion would remain reversible. But a third gravitational participant changes the balance by absorbing part of that energy. The mathematics no longer closes symmetrically. For a brief interval, the object's trajectory bends more sharply than solar gravity alone can produce. Some of the kinetic energy that would have carried it back into interstellar space transfers elsewhere, into the motion of Jupiter or the neighboring star. And suddenly the orbit no longer escapes. No explosion marks the transition. No collision occurs. Nothing visible announces that anything extraordinary has happened. The universe simply rearranges motion through gravity until what was once an open line becomes a closed ellipse. A wandering planet becomes bound. The new orbit is enormous, tilted, and elongated, preserving the memory of the encounter that created it. One complete circuit around the sun will now require roughly 25,000 years. Before human civilization exists, the object will complete approximately 200,000 of these distant loops. The solar system surrounding it is still changing violently. Giant planets migrate outward. Asteroids collide continuously. The Kuiper belt reshapes itself under gravitational instability. Comets scatter in every direction. But the captured object remains far beyond most of that chaos. Orbit after orbit, age after age, it circles a star that did not create it, while the inner planets slowly evolve toward oceans, atmospheres, and eventually, observers capable of recognizing that one distant world does not belong where it is. There is a quiet difficulty in thinking clearly about 2017 OF 201. Not because the physics is complicated, because the implication feels unfamiliar. If the capture hypothesis is correct, this object has experienced something no planet in the known solar system has ever experienced. Long before it began circling the sun, it orbited another star entirely. It once moved through a different planetary system, under different skies, around a source of light that may no longer exist anywhere in recognizable form. It belonged somewhere else first. At some point billions of years ago, that first system vanished from its life. Perhaps the planets were scattered apart through instability. Perhaps the parent star swelled into a red giant and consumed its inner worlds. Perhaps it exploded as a supernova and erased the system completely. But this one object endured. Now it drifts through the outer darkness of a second solar system, moving slowly toward a star that did not form it, carrying chemistry and geology assembled under another sun. At approximately 90 astronomical units from Earth, it circles quietly through regions humans only recently learned how to observe. The asymmetry is difficult to ignore. The first star system may be gone forever, dispersed into the wider galaxy through stellar motion and gravitational scattering. Yet, one frozen remnant remains intact, preserved by distance and cold, while the rest disappeared. A survivor without context. Its age deepens the strangeness further. 2017 OF 201 may have formed before Earth existed, inside a molecular cloud already enriched by earlier generations of dead stars. The atoms within it were forged through repeated cycles of stellar birth and destruction long before the sun ignited. Even the timescales resist intuition. If we define a human generation as 30 years, and the object was captured approximately 4 billion years ago, then it has orbited the Sun for roughly 133 million human generations. The number grows too large to picture clearly. It becomes abstract long before it becomes comprehensible. During those orbits, Earth assembled from collisions and dust. Oceans condensed. Single-celled organisms emerged, evolved, diversified, and transformed the atmosphere. Entire branches of life appeared and vanished. Human civilization rose within the smallest fraction of its current orbit. And through all of it, the object remained where it was, cold, silent, unnoticed. But after 4 billion years, the question of belonging becomes complicated. Origin matters in astronomy because it explains formation. Yet, history matters too. 2017 of 200, one has spent vastly more time orbiting the Sun than it ever spent near its original star. So, what defines where a world belongs? The universe rarely preserves clean boundaries. Galaxies merge continuously. Stars exchange material inside birth clusters. Rogue planets wander between systems. Even the atoms in your body were forged around stars that died before the sun formed. Perhaps the deeper pattern has always been exchange. And among all the objects humanity has discovered so far, this one may hold a uniquely lonely position. Not a passing visitor, not a temporary capture, a permanent resident that arrived as a stranger and quietly stayed. For most of modern astronomy, the solar system has been described as a family with a single origin. The assumption seemed reasonable. 4.6 billion years ago, a cloud of gas and dust collapsed under gravity, flattened into a rotating disk, and formed the sun at its center. Everything else emerged from the remaining material. The planets, moons, asteroids, and comets were understood as local products of the same event, connected not only by gravity, but by shared birth. A closed system. But 2017.OF 201 complicates that picture in a quiet and important way. If the capture hypothesis is correct, then this object is gravitationally bound to the sun while having formed somewhere entirely different. It belongs here physically, but not historically. That distinction matters because every major model of the outer solar system assumes native origin. Orbital distributions, chemical populations, migration histories, resonance structures, and impact rates are all interpreted as consequences of our own protoplanetary disk evolving over billions of years. Introduce even one extrasolar object, and the assumptions begin to shift. A captured world carries information that did not originate in the solar system. Its orbit may preserve the geometry of another stellar environment. Its chemistry may reflect different elemental abundances. Its internal structure may encode formation conditions that never existed around the sunday. The object becomes both participant and outsider. But the implications widen further if 2000 17 OF201 is not unique. The Vera Rubin Observatory may eventually reveal dozens or even hundreds of similar bodies occupying the distant outer regions beyond Neptune. If that happens, then part of the solar system's architecture is borrowed. Not metaphorically, literally. The young sun formed inside a dense stellar cluster where neighboring systems passed within distances small enough for gravitational exchange. During that period, stars likely captured and lost material continuously. Objects ejected from one system drifted into another. Small, icy bodies crossed between stars before planetary systems fully stabilized. The solar system would no longer resemble an isolated household. It would resemble a participant in a crowded galactic ecosystem. This possibility changes how we think about planetary formation generally. Textbook diagrams often present stellar systems as neatly separated structures, each enclosed within clear boundaries. But gravity rarely respects such clean divisions. Birth clusters blur those edges almost immediately. The exchange may have been common from the beginning. In some sense, we already accept this idea chemically. The carbon in your body formed inside ancient stars that exploded before the sun existed. The calcium in your bones and the iron in your blood were forged through stellar nucleosynthesis long before Earth formed. We have always belonged partly to other stars. But 2017 of 201 extends that inheritance beyond atoms. It suggests that entire worlds assembled around distant suns may become lasting components of foreign systems through ordinary gravitational dynamics. Geology itself becomes transferable, and once that possibility enters the picture, the solar system stops feeling fully self-contained. Its outer darkness becomes less like a boundary and more like a shoreline, open to slow exchanges with the larger galaxy surrounding it. Distance changes scale long before it changes appearance. From where 2017 OF201 currently travels around 90 astronomical units from the Sun, the solar system no longer resembles the place we know from Earth. The bright architecture of planets and moons compresses inward until nearly everything familiar disappears into a single, concentrated region of light. The Sun remains dominant, but only barely. At 90 astronomical units, sunlight is roughly 90,000 times weaker than it is on Earth. The Sun no longer appears as a wide blazing disk filling the sky. It becomes a brilliant point, intensely bright against the blackness, yet small enough to cover with a fingertip held at arm's length. Still unmistakable. Its apparent brightness from that distance would resemble the full moon seen from Earth more than the sun we experience every day. Shadows would exist, but faintly. Illumination would feel thin and distant, stretched across a gulf of frozen space. The Earth would be invisible, not merely difficult to detect, but completely lost within the sun's glare. From 90 astronomical units, the orbital spacing between the rocky planets collapses almost entirely. Mercury, Venus, Earth, and Mars would all occupy a tiny fraction of a degree near the Sun, their individual identities erased by distance. The inner solar system becomes a single crowded point. Jupiter and Saturn fare slightly better. Their immense sizes allow them to remain visible as bright moving stars near the Sun, distinguishable mainly through patient observation of their motion against the fixed stellar background. Uranus and Neptune fade further into obscurity, dim and slow in the cold outer darkness. But the silence matters more than the light. No spacecraft has visited 2017 OF201. No human transmission was intentionally directed toward it, Yet, our signals reached it anyway. Radio waves travel outward at light speed, expanding through space in all directions since the first powerful broadcasts began roughly 100 years ago. At only 0.0015 light years away, this object already sits well inside humanity's expanding sphere of radio leakage. Television broadcasts, radar pulses, military transmissions, fragments of music, compressed voices, all of it has already washed across its frozen surface, unnoticed, unanswered. The galaxy beyond would appear unchanged. Even at 90 astronomical units, the shift in perspective relative to the Milky Way's roughly 100,000 light-year diameter is effectively zero. The dense river of galactic starlight crossing the sky would look exactly as it does from Earth. That comparison quietly reveals the true scale involved. The entire solar system remains microscopic compared to interstellar space. Proxima Centauri, the nearest star, lies 4.24 light years away, around 268,000 astronomical units. Even at its most distant point of 1,600 astronomical units, 2017 OF 200, one has crossed less than 1% of the distance to the nearest star. And yet something made that crossing once. Some object moved through that vastness, entered the sun's gravitational reach, and stayed. The evidence is still there, drifting slowly above the solar system's flat planetary plane, carrying the geometry of another journey through the dark. By now, the original mystery has narrowed into something surprisingly concrete. Did the sun capture a rogue world from another star system? Based on the orbital evidence, the answer may genuinely be yes. The gravitational mechanism is understood. We have already seen capture happen elsewhere in the solar system. The birth cluster environment made close encounters common, and at the moment, no competing explanation fits 2017 OF 201 as cleanly as the capture hypothesis does. But beneath that conclusion sits a quieter question, not about astronomy alone, about motion, about belonging, about what it means for something to spend billions of years in a place it never intended to reach. The sun did not choose this object. Gravity contains no intention, no awareness. 4 billion years ago, a drifting body entered a region where multiple gravitational fields overlapped, and the mathematics of motion changed shape. What had been an open path through interstellar space became a closed orbit around a different star. Nothing decided it. The object itself had no choice either. It simply obeyed forces larger than itself, as every moon, planet, comet, and star in the universe does. Its history was redirected by geometry and mass and velocity, then frozen into an orbit lasting 25,000 years at a time. And still, it remained. While continents formed on Earth, while oxygen entered the atmosphere, while forests spread, vanished, and returned again, while mammals evolved and eventually learned to build instruments capable of detecting faint reflected sunlight from 90 astronomical units away, the imbalance in timescales becomes difficult to absorb. 2000, 17 OF 200. One has circled the sun for roughly 4 billion years. Humanity has known it exists for less than 10. During almost all of human history, it was already there, moving silently through the dark beyond Neptune, completing another small fraction of another orbit. Unknown. Its discovery required centuries of accumulated knowledge. Telescopes had to be invented. Orbital mechanics had to be understood. Digital imaging sensors had to become sensitive enough to detect a dim, moving point against dense star fields. Computing systems had to compare photographs taken months apart, searching for motion so slow it could easily be mistaken for stillness. All of that effort directed toward a frozen object 13.5 billion kilometers away. And once we found it, we immediately began asking where it came from. That instinct matters. Science is partly the discipline of refusing to ignore strangeness. A single orbit pointing the wrong direction becomes enough to reorganize years of assumptions. A faint object in archived telescope images becomes enough to reopen questions about how solar systems form, exchange material, and evolve together inside the galaxy. But some answers may remain permanently incomplete. We may never identify the star that formed this world. The Milky Way contains hundreds of billions of possibilities, all moving through time together, erasing their own histories as they drift apart. That uncertainty is not a flaw in the investigation. It is an honest boundary imposed by distance, time, and the finite information the universe leaves behind. And sometimes, that is the deepest answer available. Out beyond Neptune, beyond the recognized architecture of the planets, a small dark world continues its slow descent toward the Sunday. 2000, 17 of 200, one is, in the simplest physical sense, a sphere of rock and ice, roughly 700 kilometers wide. It completes one orbit every 25,000 years. It travels through a region so distant that sunlight arrives thin and weak, barely touching the frozen surface before scattering back into the dark. And yet it may be the only known object in the solar system that was born somewhere else. At this moment, its surface temperature sits near minus 230 degrees Celsius. Nitrogen, methane, and carbon monoxide remain frozen solid across the crust. Reddish tholins coat the exterior, complex organic residues built slowly through billions of years of ultraviolet radiation and cosmic ray exposure. Nothing moves there quickly. Impact craters remain preserved for spans of time longer than multicellular life has existed on Earth. No rain falls, no wind reshapes the terrain, no tectonic process renews the surface. The landscape simply accumulates history, layer after frozen layer, in silence almost impossible to imagine from within the warmth of Earth's atmosphere. The chemistry it carries is older than the solar system itself. The carbon, hydrogen, oxygen, and nitrogen trapped inside its ices, condensed from ancient interstellar gas clouds before the sun formed. Those atoms passed through stellar deaths, molecular clouds, and collapsing disks before assembling into this object around a different star under a different sky. That original environment is gone now, but traces of it remain locked into the chemistry of this world, preserved by cold so deep that geological change nearly stopped altogether. Since its capture, 2017 OF 201 has completed roughly 200,000 orbits around our Sunday. Each cycle carried it inward to around 44 astronomical units, then outward again toward 1,600, again and again, for 4 billion years, unseen the entire time. But tonight, observatories on Earth continue scanning the sky. On Cerro Pachon in Chile, the Vera Rubin Observatory photographs the southern heavens every few nights, building a growing archive of motion across deep time. Within that immense stream of data, more objects like this one are almost certainly waiting. Worlds with wrong orbits. Worlds detached from familiar gravitational histories. Worlds suggesting that the outer solar system is not solely a record of the sun's formation, but partly a record of the galaxy passing material back and forth between young stars. If capture happened once, it was probably never unique. Nearly every star forms inside crowded stellar nurseries. Nearly every young planetary system experiences instability, ejection, migration, and close encounters. The boundary between one solar system and another was never fully closed. It only appeared that way from the inside. And so, the story comes to rest with a frozen object 90 astronomical units away, descending slowly along a path that began around another sun before Earth existed, carrying through the dark a chemical memory older than our world, now finally noticed by the civilization that happened to look up at the right moment and ask what it was.